Yani hiç çıkan gitmez nasıl değil yani.
Böyle İngilizce.
Tamam.
Herkese merhabalar. Bugün Güngör Çin Bilimler Akademisi'nden geliyor. Can'ı ben tabii Doktor Engin'den tanıyorum. İkisi de. Başarılı, çok çalışkan bir arkadaşlar. Şimdi bir güzel çalışmalar Çin'de devam ediyor. Özellikle bu HXMT isimli bir uydu var. Onunla ilgili ondan yapmaya çalışıyor. Şimdi bugün kendisize partial equation, propeller stage of Aquila X-1 diye bir konuşmaya anlatacak. Biraz da uydu ile ilgili bilgi verecek diye umuyorum.
Teşekkürler. First of all, I would like to thank Paul GÜNGÖR for inviting me here to give this talk. It's a really good opportunity for me. So the title of my talk is Partial Equation in the Propeller Stage of Aquila X-1. I shortened my title a bit and the announced one to be more specific. This is the outline of my talk. So first part is my PhD work. So since I'm in a science team of a satellite called Insight-HXMT now, at the second part I will try to give a very brief introduction about our satellite, and I will present very preliminary results from our satellite as well. So this is the outline. First, I will try to introduce long and 6-8 binaries and accreting millisecond X-ray pulsars. And then I will try to explain a classification based on luminosity that we made actually in my PhD thesis, and so on. Let's start. So long and 6-8 binaries, actually it will be easier to give me this talk in an astrophysics department, astronomy department, because I think you all know what long and 6-8 binaries and accreting millisecond pulsars are. So long and 6-8 binaries are binary systems containing a compact object. It can be a black hole or a neutron star, and a long mass companion. It's also called donor star, since the material comes from that star onto the other one. The accretion mechanism in these kind of systems is Rorschach overflow. So in the next slide you will see an animation by NASA, and you will better visualize what is. They are relatively old systems. They are observed in galactic disk, bulge, and globular clusters, and they have relatively low magnetic fields. These systems are very important systems because of this. Because as we all know, pulsars are born in supernova explosions with its the fastest spin periods of their entire life, and losing their angular momentum, they spin down. And if we observe a pulsar in an old system, it might have slower spin period. But these kind of systems have fast spin period or frequency in other words. So which means that accretion onto the neutron star does not only accrete matter, but also transfers angular momentum, so the star spins up. So in this movie you will see this. Anyway, let me explain what it is. This is a donor star. It feels its Rorschach, and then from the first Lagrange point, it starts to accrete matter to the Rorschach of the compact object. At the center, there is a neutron star. It can be a black hole as well, but in my case, it's a neutron star. Since this star has spin and also a motion in the orbital, the material has angular momentum, so the material creates an accretion disk around the neutron star, around the compact object. So, according to the location of the inner radius, the material can be transferred onto the pole of the neutron star, and we see X-ray luminosity. So basically the X-ray luminosity that we observe is the gravitational potential energy of inflowing material onto the neutron stars. Okay, at 20 milliseconds in the lowest X-ray binaries, we don't see pulsations in X-ray band. So, at 20 millisecond X-ray pulsars are a subset of lowest X-ray binaries. There's only 19 members in this group, and total lowest X-ray binary population is more than 200. And they show oscillations in X-ray band. So this specialty differs from lowest X-ray binaries. And they have relatively high spin frequencies. And maybe the most interesting cases are intermittent pulsations. Because on a triode system, overall these 19, they don't show pulsations all observation period. They show pulsations only for a limited time duration. And again, maybe the most interesting case is Aquila X-1. Aquila X-1 showed oscillations only for 150-second part, overall 22 years observation. So we observed it for 22 years, only for 150-second pass, it showed oscillations. And this is still an open question. But actually, it's correct, because the spin period of Aquila X-1 was already known from burst oscillations. So Aquila X-1, let's introduce to you what Aquila X-1 is. It's a low-mass star, and it's most of the time in its quiescence period, and not periodically, but mainly cyclically, it shows outbursts. And during outbursts, it can reach up to 10 to the 35, 36 erg per second. So this is 22 years life curve of this source. And in these ups, it shows a fast rise and exponential decay phases. So this calls Fred type of outburst. There are also some low intensity states which has more energy than the quiescence period, but it does not follow a pattern like this. So what I first do is I calibrated all of the outbursts according to the beginnings of the outburst, and I saw this picture. So the outburst was not distributed to this picture randomly. It is connected to 3 different groups, and I classified as high long outburst, which has duration up to 60 days, and the peak count rate is about 61, maximum 61 count per second. And the other is medium low outburst and the short low outburst. So there were different classifications in the literature before, but it was not based on light curve pattern or based on duration and peak count rate of an outburst. So this is only done by us for now. And to see what is the difference between different type of outbursts, we took our observations and we analyzed the data, and we see the physical parameters evolve in the same way. The only different one is the flux. This shows us the reason of the outburst is the same physical phenomena, but it is done with different powers. And I published this in 2014 in Manuals. And I also, yes?
What's the telescope there?
This one, RECE. Actually, I don't want to give all the details of this because I want to explain another thing today, so this is just for starting. And I also checked, look, these lines show pre-outburst quiescence period. So this curve is, we also checked if there is a relation between peak count rate and pre-outburst quiescence duration. So we see this picture. So not low intensity state, but thread type of outburst has slightly correlated with the pre-outburst duration time. It's something like in an earthquake area, if you don't see any earthquake for a longer period, upcoming earthquake can be more energetic. It's something like that. So longer waiting time means this reservoir fills by more material, and the upcoming outburst can be more energy. But of course, the separation, the fluctuations on this curve means that this is not the only reason. There must be different reasons, but it is somehow correlated with this. We also published this in a small new astronomy paper.
Are these also explained by this instrument?
Exactly, exactly. Now I'm coming to that. So, before to pass the other word, what I would like to explain today, I have to describe a few critical radii. One of them is light cylinder. Light cylinder is the cylinder centered on the pulsar and aligned with the rotation axis, at whose radius rotating speed equals to the speed of light. In other words, this is the maximum distance which material and the magnetic field can be interacted. If any material is out of this cylinder, it cannot interact with the magnetic field. And the rotation radius, this is the radius that angular velocity of the star is equal to Keplerian angular velocity, and it's described by this. I will use these equations in upcoming slides. So Pascal's parameter is a ratio of angular velocity of the star to the Keplerian angular velocity at the inner disk radius. And it's described by this. I will come to this part later. It's also equals to this. And the outline radius is the radius where the magnetic stresses and the material stresses are balanced. And it's also described as this. We will use these equations later. So, these magnetosphere interaction stages are separated to three different parts, and according to the position of inner disk radius. So, if the inner radius of the disk is other than the light cylinder, which means material and the magnetic field will not be interacted, and then we will not see any accretion onto the neutron star. So, there is no accretion, and also there is no evidence of the disk existence in the X-ray light curve. And the propeller stage, if we assume a thin disk, and if inner radius of the disk is closer than the light cylinder, which means this material and the magnetic field will be interacted, but because of the propeller effect, the material will not follow the magnetic lights and fall onto the neutron star, if we assume a thin disk. But if it is a thin, thick disk, if the inner layers of the disk has a scale height, then maybe some fraction of the disk material can fall off the neutron star. And when I show the thread type of outburst, it has a fast rising phase and exponential decay stage. And in the exponential decay stage, somewhere at the middle, there is a need, which is a transition from slow decay stage to fast decay stage. I will also show this later on. And if the inner radius of the disk is closer to the corrotation radius, inner than the corrotation radius, all of the material reaching inner layers will fall onto the neutron star. So this is the accretion stage now. Yeah, this is fast rising exponential decay, a typical light curve of thread type of outburst. A fast rising, we are not interested in that part now, and exponential decay stage. And here there is a need, which the decay trend is changing dramatically back from slow decay stage to fast decay stage. And in some papers, this need is linked with the transition from accretion stage to propeller stage. So my whole model depends on this assumption. So basically, if this is correct, which means here all of the material reaching inner layers of the disk falls on the neutron star. So after here, still material comes to the inner layers, and the inner radius of the disk is around co-rotation radius. Some fraction of the material reaching inner layers will fall on the neutron star. So what did we say? The X-ray luminosity that we observe is the gravitational potential energy of inflowing material. So here, if all of the material reaches, this trend gives us, let's say, m dot star, also m dot, which means the material reaching inner layers equals to the material reaching to the pole of the neutron star. Here, not all of them, but fraction. So, basically, if we fit this slow decay path, this gives us m dot time evolution of the material reaching inner layers. We have another assumption, m dot t, the time dependence of the m dot, follows the same trend to the propeller state. This is an assumption. And if you take the ratio of this to somewhere on that exponential curve, we reach a ratio which gives us the fraction of inflowing material onto the neutron star to the material reaching inner layers. So basically, this is a unitless function. As we know, Aquila X-1 shows different light curve pattern with different energies. Since we can describe the light curve with a unitless function, then we are allowed to compare different outbursts in a unitless parameter in the y-axis. But now we have to also obtain a physical parameter, which is a unitless parameter, to compare duration axis, x-axis. Since we know outburst pattern can be differently and outburst duration can be different. So using a combination of formula, co-rotation radius and inner radius of the disk, we obtain this fastness parameter. And using the alpha and radius formula, we also obtain this. And when we put this formula, using this to here, we obtain fastness parameter as a function of m dot and m dot co-rotation. M dot co-rotation means the mass ratio falling onto the neutron star when exactly inner radius of the disk is located at the co-rotation radius. And from here, luminosity is directly related to m dot star. M dot star is mass ratio falling onto the star. And that is mass ratio reaching inner layers. Here, m dot co-rotation will be directly related to the critical luminosity of the need in the decay stage. So upper panel also shows, upper part also shows us the exponential function that will fit the slow decay stage. So this ratio is also gives us a fastness parameter as a function of time. Fastness parameter is also a unitless function. Then we have two parameters, both unitless. Then we can compare different outbursts. But both depends on time. So we can parametrically plot this function in time. So fastness parameter is only variable in this equation is time. Again here, the only variable is time. We can parametrically plot this. But before this, what we expect? We expect basically a step function, which means the inner layers of the disk move toward the neutron star, while this If the inner radius of the disk is older than rotation radius, none of the material will fall on the neutron star. After past the rotation radius, all of the material will fall on the neutron star, and since the inner layers lose material, the inner layers will start to shrink back, and after it passed rotation radius again, we expect none of them will fall on the neutron star. So we expect a step function. But what we say in the beginning of my talk, if the inner layers of the disk has a scale of height, then it will be a smoothed step function. So this is a smoothed step function. Tangent hyperbolic is a smoothed step function, and this delta describes how smoothed is that. So this delta must be related with the scale height of the inner layers of the disk. So I took these light curves from Campana et al. This is our step function, this is spacing parameter, and this is the function describing slow decay stage. This is logarithmic scale. In logarithmic scale, we see this knee much better. So I fit slow decay stage using this function. And after I obtain a good fit, and then I multiply this function with the step function, and then I fit all the decay stage using this function multiplied by smoothed step function. So this gives us first the delta, which is a kind of key to scale height of inner layers. And we also get the critical luminosity, if it is a free parameter in our model. And most of the part it was. So we can describe the light curve quite well. But what we assumed the X-ray luminosity that we observe is the gravitational potential energy of inflowing matter. But there is a source there, and the source has this around it. And sorry. In these kind of systems, magnetic field is quite low. So the disk can reach almost to the surface of the neutron star. So when we observe a source, the inner layers of the disk can also contribute to X-ray luminosity. So to apply our model, we have to somehow separate the light caused by neutron star pole and the inner layers of the disk. So we took RxD PCA data again from different type of curves of Aquila X-1, and we fit the spectrum using a combination of black body, disk black body, and a Gauss. Gauss can be necessary for the iron line there. Black body represents the neutron star poles, and this black body represents the inner layers. After we fit all the spectra, we obtain flux only for black body component. Then we got the light curve only for the neutron star pole, which will give us the time evolution of the n dot star, the material reaching onto the neutron star. So this is an example of the spectra, and this is the result. So the upper panel shows the time, temperature, black body temperature. This is hardness parameter, which shows the state transitions, and this is the light curve. As you see, the knee is simultaneous with the state transition. And this is different type of outputs also. This is the output list of our parameter. But there is an anomaly here, which is very high temperatures. These temperatures cannot be explained via physical processes. So, which means our model there is wrong. So we have to find better model for these parts. As you can see, these temperatures are very high. In this low equation, a quantization cloud also contributes, quantization cloud around the neutron star also contributes to the X-ray luminosity. Then we have to also take into account quantization cloud. Then we also added a quantization component here without quantization. When we add the quantization component, the temperatures becomes normal, except only these two data where the mean are. But we see the same anomaly also here, around here. So which means if we see the propeller effect, actually in the literature no one talked about the propeller effect in the rising stage because of different instabilities. They always talk about the propeller effect in the decay stage. But if you see the propeller effect while the inner radius of this is shrinking back, why not we see the same effect while the material moves to the neutron star? But of course it happens much quicker rate. So I just put a question mark here. Maybe we see propeller effect also in the rising stage. So, and then we applied our model to all the light curve that we obtained. Okay? And this is the final picture. The y-axis is m dot star over m dot, which is the mass fraction rate falling on the neutron star to the mass fraction reaching inner layers and to the fastness parameter. It's a step function, it's a smoothed step function, but again what we expect for a unit system has same magnetic field, so the corrotation radius located at the same place, and the disk material Rorschach size is same. We have to see the same step function for a unit system. It must be different system-wise, but for a unit system, we see the same step function for all different type of outbursts. Even if they have long duration, they have higher peak, lower peak, it doesn't matter. In this picture, it follows the same trend. So, before 0.9, all of the material falls on the neutron star. Here in the propeller stage, a fraction of the material falls on the neutron star, and here none of them falls. The physical phenomena behind this picture is this. And we also published this work in Aquila. Before I pass this, I can take some questions about propeller method.